And now in this lecture we'll find out the area of the green shape. In the drawing we have a quarter circle. AOB is a quarter circle, and we have also tangent QP that is tangent to this quarter circle here at this point. This is angle AQP that is equals to 90 degrees in its side, and this is angle APQ that is also a right angle, is equals to 90 degrees in its size. BQ equals to 3 units in its length, AP equals to 6 units in its length. Again, our mission is to find out the area of this green shape. We define the point of tendency of tangent PQ with this quarter circle, this point is point S. In the next step, we join points O and S together by a straight line. What is the definition of line segment OS? Line segment OS starts from point O, that is the center of the quarter circle, and ends at point S, that is the point on the quarter circle itself. This is exactly the definition of a radius. Therefore, OS is the radius of this quarter circle. So we define the radius of this quarter circle as x. Therefore, OS equals to x, that is the radius of the quarter circle. So I write it down, OS equals to x. Here we can implement rule 1. The radius OS is known to point S, that is the point of tendency of tangent QP with this quarter circle. And whenever you have a radius that is known to the point of tendency, then tangent QP will be perpendicular to the radius SO. If QP is perpendicular to SO, it means that this angle equals to 90 degrees. And this angle also equals to 90 degrees according to rule 1. In the next step, we will do a construction, that is to say from point B, we will draw perpendicular on OS. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point B and OS, this point is M. So inside quadrilateral MBQS, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. 270 degrees plus the size of this missing fourth angle. In total, they must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this missing fourth angle must be equal to 90 degrees in its size. So inside quadrilateral MBQS, we have 4 right angles. Any quadrilateral that has 4 right angles must be at least a rectangle, if not a square. So we relate to this quadrilateral MBQS as a rectangle. And you know that the opposite sides of a rectangle are equal to each other. So in rectangle BMQS, side BQ equals to side MS. BQ equals to MS, but BQ equals to 3, therefore MS must be also equal to 3 units in its length. So I write it down. Side MS equals to 3 units in its length. So we also have the rule that the opposite sides of a rectangle are parallel to each other. So in rectangle BMQS, side BQ is parallel to the opposite side MS. So I write it down. In rectangle BMQS, side BQ must be parallel to the opposite side MS. Repeat again. In rectangle BMQS, side BQ must be parallel to the opposite side MS. So here side MS is part of OS. OS is the radius of the quarter circle, therefore it is absolutely a straight line. OS is a straight line, so MS is part of OS. Again, MS is part of OS and MS is parallel to BQ. So if part of a straight line is parallel to another straight line, then the straight line itself must be also parallel to the other straight line. Here, part of the straight line OS, that is MS, is parallel to BQ. Therefore, the straight line OS itself must be also parallel to BQ. Okay, the straight line OS must be also parallel to BQ. So I'll write it down. The straight line OS must be also parallel to BQ. So in quadrilateral OBQS, side OS is parallel to side BQ. Therefore, quadrilateral OBQS is a trapezoid. So I write it down. Quadrilateral OBQS is a trapezoid. Why? Because it has one pair of parallel sides. What is the length of line segment OM? From the drawing it is very easy to see that OM equals to OS minus MS. Again, OM equals to OS minus MS. So I write it down. OM is equals to OS minus MS. So OM equals to OS, that is X, it is the radius of the quarter circle that is equal to X according to our definition, minus MS. MS is 3. So in conclusion, found out that OM equals to X minus 3 units in its length. This is 9 segment OM. This is equals to X minus 3 units in its length. So I write it down. 9 segment OM is equals to X minus 3 units in its length. In the next step, we will do another construction. That is to say, from point A, we will do perpendicular on OS. Again, from point A, we will do perpendicular on OS. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point A and OS as M. So inside quadrilateral ANSP, we have 1, 2, 3 right angles. Therefore, the fourth angle must be also equal to 90 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. So inside quadrilateral ANSP, we have 4 right angles. Any quadrilateral that has four right angles must be at least a rectangle, if not a square. So we relate to this quadrilateral ANSP before right angles as a rectangle. And we also know that the opposite sides of a rectangle are equal to each other. That is to say, side AP equals to side NS in rectangle ANSP. So AP equals to NS, but AP equals to 6, therefore NS must be also equal to 6 units in its length. So I'll write it down. NS equals to 6 units in its length. NS equals to 6 units. So we have another rule that I've already mentioned, that the opposite sides of a rectangle are parallel to each other. So in rectangle NSPA, side NS must be parallel to side AP. So I write it down. In rectangle ANSP, side NS or side AP must be parallel to side NS. SAP is parallel to NS. Repeat again. In rectangle ANSP, side AP must be parallel to side NS. NS is part of the straight line OS and is parallel to AP. Therefore, the straight line OS must be also parallel to AP. The straight line OS must be also parallel to AP. According to the same rule, that if a part of a straight line is parallel to another straight line, then the straight line itself must be also parallel to the other straight line. Part of the straight line OS, that is NS, is parallel to AP. Therefore, the straight line itself OS must be also parallel to AP. The straight line OS must be also parallel to AP. Therefore, quadrilateral OSPA is a trapezoid. Why? Because it has one pair of parallel sides. Side OS is parallel to side AP. So I write it down. Quadrilateral OSPA is a trapezoid because it has one pair of parallel sides. Repeat again. I found out actually that quadrilateral OSPA is a trapezoid. So in conclusion, we found out that quadrilateral OBQS is a trapezoid, and also quadrilateral OSPA is also a trapezoid. So the sum of the areas of those two trapezoids will give us the area of this shape in total, the whole shape, OBQPA. Okay, because of the fact that this big shape consists of those two trapezoids. Therefore, the sum of the areas of those two trapezoids will give us the area of this shape in total. Okay. So what is the length of line segment ON? What is the length of this line segment ON? From the drawing, it is very easy to see that ON equals to OS minus NS. Again, ON equals to OS minus NS. So I write it down. ON equals to OS minus NS. So ON equals to OS, that is the radius of the quarter circle, that is equal to X minus NS. We already found out that NS equals to 6. So we already found out that the length of line segment ON, it is actually equals to X minus 6. So we can write down here that ON is equals to X minus 6 units in its length. Okay, and OM equals to X minus 4 units. Okay, so in the next step we will define this angle AON. We define this angle as alpha. And we will focus on the right angle AON. In the right angle AON, this angle equals to alpha, this angle equals to 90 degrees. Therefore, the missing angle here must be equal to 90 degrees minus alpha, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. So, we will define 90 degrees minus alpha as beta, and therefore the missing angle here will be equal to beta according to our definition. Okay. If 90 degrees minus alpha equals to beta, it means that 90 degrees minus beta will be equal to alpha. If you add to this equation alpha and subtract beta, we will arrive to this equation that 90 degrees minus beta equals to alpha. Okay. So, what is the size of this angle? The size of this angle is equal to the size of the big angle AOB, that is a right angle, is equal to 90 degrees, minus the size of this angle, that is alpha. Again, angle AOB, that is a right angle, that is equal to 90 degrees, minus this angle, that is alpha, is equal to the missing angle MOB. So the missing angle MOB equals to 90 degrees minus alpha. But according to our definition, 90 degrees minus alpha equals to beta. Here, 90 degrees minus alpha equals to beta, so the missing angle here equals to beta. The missing angle equals to beta. In the next step, we'll focus on this right angle triangle OMB. In the right angle OMB, this angle equals to beta, this angle equals to 90 degrees. Therefore, the missing angle here must be equal to 90 degrees minus beta. Here, the missing angle must be equal to 90 degrees minus beta. But 90 degrees minus beta equals to alpha. Here you can see that 90 degrees minus beta equals to alpha, so the missing angle here equals to alpha. So I write it down. In the next step, we'll prove that those two right angles can join to each other. That is to say, we'll prove that this right angle OBM is congruent to this right angle, that is actually a triangle ONA. We'll prove that the right triangle ONA is congruent to the right triangle OBM. Before that, what is the definition of line segment OA? Line segment OA starts from point O, that is the center of the quarter circle, and ends at point A, that is the point on the quarter circle itself. This is exactly the definition of a radius. Therefore, OA equals to X, that is actually the radius of the quarter circle, according to our definition. Likewise, OB will be also the radius of the quarter circle. Why? Because it starts from point O, that is the center of the quarter circle, and ends at point B, that is a point on the quarter circle itself. Therefore, OB is also the radius of the quarter circle, that is equal to X units, according to our definition. So, as I already mentioned, in the next step, we prove that those two right triangles can go into each other. So, this is the right triangle ONA. And we prove that this right triangle ONA is congruent to this right triangle, triangle OBM. So why those two right triangles can go into each other? First of all, those two angles, they are both equal to 90 degrees, therefore they are equal to each other. So this angle is angle ONA in the right triangle ONA, and it is equal to this angle. This is actually angle OMB in the right triangle OBM. Repeat again. Angle ONA in the right triangle ONA equals to angle OMB in the right triangle OBM. They are both equal to 90 degrees, therefore they are equal to each other. In addition, those two angles, they are both equal to alpha, therefore they are equal to each other. So this is angle AON in the right triangle ONA, and it is equal to this angle, that is actually angle OBM in the right triangle OBM. So I repeat again. Angle AON in the right triangle ONA equals to angle OBM in the right triangle OBM. They are both equal to alpha, therefore they are equal to each other. And we have those two angles, they are both equal to beta, therefore they are equal to each other. So this is angle OAN in the right triangle ONA, and it is equal to this angle, that is actually angle MOB in the right triangle OBM. Repeat again. Angle OAN in the right triangle ONA equals to angle MOB in the right triangle OBM. They are both equal to beta, therefore they are equal to each other. And finally, side OA in the right triangle OAN is equal to this side OB in the right triangle OBM. They are both the radii of the circle that is equal to X, therefore they are equal to each other. Repeat again. side OA in the right triangle ONA equals to side OB in the right triangle OBM. They are both equal to x, therefore they are equal to each other. They are both the area of the circle that is equal to x, therefore they are equal to each other. So we actually proved that the right triangle ONA is congruent. This is the sign of congruent to the right triangle OBM according to angle side angle rule. So what is angle side angle rule? Angle side angle rule is that if you prove that two angles and the side that included between the two angles in one triangle are correspondingly equal to two angles and the side that included between the two angles in a second triangle, then you actually proved that the two triangles can go into each other according to angle side angle rule. And we actually proved that in the right triangle ONA, those two angles alpha and beta, and the side that included between those two angles, that is side OA, are correspondingly equal to those two angles that are alpha and beta, and the side that included between those two angles, that is side OB in the right triangle OBM. Therefore, we actually proved that those two right triangles can go into each other according to angle side angle rule. And from the fact that those two right triangles can go into each other, we will derive that side ON in the right triangle ONA is equal to side MB in the right triangle OBM. Repeat again. From the fact that the two right triangles can go into each other, we derive that side ON in the right triangle AON is equal to side MB in the right triangle OBM. Actually, those two sides, they are equal to each other according to the rule that corresponding sides in congruent triangles are equal to each other. Those two right triangles can go into each other, therefore the two corresponding sides, that is to say those two corresponding sides, must be also equal to each other. But we have already found out that ON, side ON equals to x minus 6. Side ON equals to x minus 6. So we can write here that ON equals to x minus 6. And from this equation, x minus 6 equals to ON equals to MB. We derive that side MB is also equals to x minus 6 units in its length. MB equals to x minus 6 units in its length. So we can write down in the original drawing that side MB equals to x minus 6 units in its length. Likewise, because of the fact that those two right triangles can go into each other, we will derive that side OM in the right triangle OMB is equal to side NA in the right triangle ONA. Side OM equals to side ON, side OM equals to side NA according to the rule that corresponding sides in congruent triangles are equal to each other. But we have already found out that side OM equals to x minus 3. Here, side OM equals to x minus 3. So we can write here that OM equals to x minus 3. And from this equation, x minus 3 equals to OM equals to NA, we will derive that NA is also equals to x minus 3 units in its length. Okay, NA equals to x minus 3 units in its length. NA equals to x minus 3 units. So in the next step, I will copy the right angle ONA in a new page, and we'll implement on this right angle ONA the Pythagoras theorem. Again, side NA equals to x minus 3. We already found out that side ON equals to x minus 6. Here ON equals to x minus 6. And the hypotenuse OA is the radius of the quarter circle that's equal to x. So here by PT is the proportion for Pythagoras theorem. According to the Pythagoras theorem, in any right angle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. In the right angle ONA, the hypotenuse is OA, therefore the square of the hypotenuse is OA squared, and it must be equal to ON squared plus NA squared. OA is x, therefore OA squared is x squared, and it must be equal to ON squared. ON is x minus 6, therefore ON squared is x minus 6 squared plus NA squared. NA is x minus 3, therefore NA squared is x minus 3 squared. So in conclusion, we found out that x squared equals to x minus 6 squared plus x minus 3 squared. Here we'll open the brackets on this side of the equation, and we will get that x squared equals to x minus 6 squared. X minus 6 squared equals to x squared plus 6 squared, that is 36, minus 2 times x times 6, that is minus 12x, plus x minus 3 squared. X minus 3 squared equals to x squared plus 3 squared, that is 9, minus 2 times x times 3, that is minus 6x. So here we have x squared on both sides of the equation, so x squared will get cancelled. After we cancel the x squared, in this side of the equation we left with nothing. So it is 0, that is equal to, here we have 36 plus 9 is 45. And maybe minus 12x minus 6x is minus 18x plus x squared. In conclusion, we found out that x squared minus 18x plus 45 equals to 0. So this is a quadratic equation, and the general formula for quadratic equation is ax squared plus bx plus c equals to 0. This general formula, a, b, and c are the coefficients of the quadratic equation, and x is the variable that we are looking for. And we find out the value of x according to the following formula. X equals to minus b plus minus square root of b squared minus 4 times a times c over 2a. In our specific quadratic equation, x squared minus 18x plus 45 equals to 0. The coefficient a equals to 1. The coefficient b equals to minus 18. And the coefficient c equals to 45. So, in the next step, we'll put the data inside the general formula for x, and we'll find out the value of the values of x. So, according to the general formula, x equals to minus b. B is minus 18, therefore minus b is minus 18, that is plus 18. Plus minus square root of b squared. B is minus 18, therefore b squared is minus 18 squared, that is 324. Minus 4 times a is 1, so minus 4 times 1 is minus 4 times 45. Minus 4 times 45 is minus 180 divided by 2a. A is 1, so 2a is 2 times 1, that is 2. So, we found out actually that x equals to 18 plus minus the square root of 324 minus 180 is 144 divided by 2. So here x equals to 18 plus minus the square root of 144 is 12 over 2. So here we have two solutions that are possible for x. The first solution for x is that x equals to 18 plus 12, that is 30, and 30 over 2 is 15. According to the first solution, x equals to 15 units. And we also have the second solution that is possible for x, that x equals to 18 minus 12 over 2. 18 minus 12 is 6, and 6 over 2 is 3. So according to the second solution, x equals to 3. But because of the fact that we have already found out that BM, side BM or line 7 BM equals to x minus 6. BM equals to x minus 6. We have already found out that line 7 BM equals to x minus 6 units in its length. So BM is a length, and as a length it must be a positive number. Must be a positive. That is to say, the length BM equals to x minus 6. The length of BM is x minus 6. So the length x minus 6 must be a positive number. That is to say, it must be greater than 0. If x minus 6 is greater than 0, it means that x is greater than 6. X is greater than 6. If x is greater than 6, it can never be equal to 3, because 3 is less than 6. Okay? X can never be equal to 3 because x must be greater than 6. Therefore, this solution is incorrect solution. We will cancel the solution, and we left only with the first solution that is possible for x. That is actually x equals to 15. X equals to 15. found out actually that x equals to 15 units in its length. In the next step, I present to you the formula for the area of a trapezoid. Repeat again, a trapezoid is a quadrilateral with one pair of parallel lines, or parallel sides. Again, a trapezoid is a quadrilateral with one pair of parallel sides. So here we have trapezoid A, B, C, D. This is trapezoid ABCD. In trapezoid ABCD, side AC is parallel to side BD. The two parallel sides, that is to say AC and BD, are defined as the bases of the trapezoid. So AC is the base and BD is also the base. So the area of trapezoid ABCD is equals to the sum of its bases. That is to say, it is AC plus BD, the two bases of trapezoid ABCD. AC plus BD times the height. The height transgress 90 degrees with the base. So this angle actually equals to 90 degrees. And this angle also equals to 90 degrees. So the height is CD. We define the height CD as h. So it is times h over 2. Repeat again. The area of trapezoid ABCD, or the area of any trapezoid, equals to the sum of its bases times the height over 2. Okay? So, what is the area of this grain shape? The area of the grain shape is equals to the area of this shape, the shape in total, the whole shape, OA, P, QA, minus the area of the quarter circle OAB. Again, the area of this shape in total, the whole shape, minus the area of the quarter circle OAB, will be equal to the area of this grain shape. But the whole shape OA PQB consists of those two trapezoids. Trapezoid OBQS and the other trapezoid, that is trapezoid OASP. So the sum of the areas of those two trapezoids will give us the area of this shape in total, and the area of this shape in total minus the area of this quarter circle OAB will give us the area of this grain shape. So in conclusion, found out that the area of this grain shape equals to the area of trapezoid OBQS plus the area of this trapezoid, that is trapezoid OSPA, repeat again, the sum of the areas of trapezoid OBQS plus the area of trapezoid OSPA will give us the area of this shape in total minus the area of the quarter circle OAB. So it is minus the area of the quarter circle OAB. Okay, so the area of the green shape is equals to the area of trapezoid OBQS. What is the area of this trapezoid OBQS? The area of trapezoid OBQS equals to the sum of its bases, that is BQ plus OS, times the height, that is QS. The height creates 90 degrees with the two other bases, so the height is QS over 2. Repeat again, we actually found out that the area of trapezoid OBQS equals to the sum of its bases, that is BQ plus OS, times the height, that is QS, over 2, plus the area of trapezoid OSPA. What is the area of this trapezoid OSPA? It is equals to the sum of its bases, that is OS plus AP, because OS is parallel to AP. We already found out that OS is parallel to AP, so it is the sum of its bases, that is OS plus AP, times the height. The height must create 90 degrees with the two bases. Here SP indeed creates 90 degrees with the other two bases. This angle equals to 90 degrees, and this angle also equals to 90 degrees. So the height is SP divided by 2. In conclusion, we found out that the area of trapezoid OSP in total, it is equals to the sum of its bases, that is OS plus AP, times the height, that is SP over 2, minus the area of the quarter circle OBA. What is the area of this quarter circle OBA? The area of any quarter circle equals to the area of the circle over 4. The area of this circle is pi x squared, because the radius is x, therefore the area of this circle is pi x squared. So pi x squared over 4 is the area of the quarter circle OAB. Okay. So the area of trapezoid OBQS equals to BQ, that is 3, plus OS, that is x, that is equals to 15, times QS. QS is x minus 6, x is 15, so 15 minus 6 is 9. So QS is 9 over 2. In conclusion, we found out that the area of this trapezoid OBQS in total, it is equals to 3 plus 15, that is the sum of its bases, times the height, that is 9 over 2, plus the area of trapezoid OSPA. The area of trapezoid OSPA equals to OS, that is 15, plus AP, that is 6, times the height SP. SP equals to x minus 3. Here SP equals to x minus 3. So SP equals to x, that is 15, minus 3. 15 minus 3 is 12. So the height SP is 12 over 2. In conclusion, we found out that in total the area of trapezoid OSPA is equal to 15 plus 6 times 12 over 2 minus the area of the quarter circle OAB. The area of the quarter circle OAB equals to pi times x squared. X is 15, therefore x squared is 15 squared, that is 225, divided by 4. In conclusion, found out that the area of the quarter circle OAB equals to 225 pi over 4 square units. So actually the area of the green shape in total will be equal to 5 plus 15, that is 18. 18 over 2 is 9, and 9 times 9 is 81. In conclusion, we found out that the area of trapezoid OBQS equals to 81 square units, plus the area of trapezoid OSPA. The area of trapezoid OSPA equals to 15 plus 6, that is 21, and 12 over 2 is 6, and 21 times 6 is 126. In conclusion, we found out that the area of trapezoid OSPA is 126 square units minus the area of the quarter circle OAB. The area of the quarter circle OAB is equals to 225 pi over 4, and 225 pi over 4 is equals to 176.716 square units. So the area of the green shape in total equals to 81 plus 126, that is 207, minus 176.716 square units, and 276 minus 176.71 square units, it is equals to 30.285 square units. In conclusion, found out that the area of the green shape is equals to 30.285 square units. Repeat again. The area of this green shape is equals to 30.285 square units. So in the next step, I will summarize the lecture. In this lecture, we found out the area of this green shape. In the drawing, we have a quarter circle, and we also have here tangent QP that is tangent to this quarter circle here at this point. This is angle BQP, that is a right angle, and this is also angle APQ, that is also a right angle. We know that side BQ equals to 4 units in its length, side AP equals to 6 units in its length. Again, our mission is to find out the area of this green shape. So in the first step, we defined the point of tendency of tangent PQ with this quarter circle. This point is point S. Then we join points O and S together by a straight line. What is the definition of line segment OS? Line segment OS starts from point O, that is the center of the quarter circle, and then to point S, that is the point of the quarter circle itself. This is exactly the definition of a radius. Therefore, OS is the radius of this quarter circle. We define the radius of the quarter circle as X. Here X is the radius of the quarter circle. So OS equals to X. This is the radius of the quarter circle. The radius OS is drawn to point S. That is the point of tendency of tangent QP with this quarter circle. And whenever you have a radius that is drawn to the point of tendency, then tangent QP will be perpendicular to the radius SO. If QP is perpendicular to SO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. Okay? In the next step, we did a construction actually. From point B, we drew perpendicular on OS. Again, from point B, we drew perpendicular on OS. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point B and OS as M. So inside quadrilateral BMQS, inside this small quadrilateral, we have one two free right angles. The sum of free right angles is 270 degrees. Actually, we have 1, 2, 3 right angles. So the sum of those three right angles is 270 degrees, plus the size of this fourth missing angle. In total, they must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this missing fourth angle must be equal to 90 degrees in its size. So inside quadrilateral BMQS we have 4 right angles, and any quadrilateral that has 4 right angles must be at least a rectangle if not a square. So we relate to this quadrilateral BMQS as a rectangle. So in rectangle BMQS, the opposite sides must be equal to each other. So side BQ must be equal to the opposite side MS. But BQ is 3, therefore MS must be also equal to 3. And we also have the rule that the opposite sides of a rectangle are parallel to each other. That is to say, side BQ is parallel to the opposite side MS. Repeat again. In rectangle BMQS, side BQ is parallel to the opposite side MS. So we know that BQ is parallel to MS. MS is part of OS. Again, MS is part of OS. OS is the radius of the quarter circle. Therefore, it is absolutely a straight line. So OS is a straight line, and part of the straight line OS, that is MS, is parallel to BQ. If a part of a straight line is parallel to another straight line, then the straight line itself must be also parallel to the other straight line. So the straight line OS must be also parallel to BQ. Okay, so the straight line OS must be also parallel to BQ. So we know that OS is parallel to BQ. So in quadrilateral OBQS, we have side OS that is parallel to side BQ. Therefore, quadrilateral OBQS is a trapezoid. Quadrilateral OBQS is a trapezoid. Why? Because it has one pair of sides that are parallel to each other. Side OS is parallel to side BQ. In the next step, we actually found out the length of this line segment OM. What is the length of OM? From the drawing, it is very easy to see that OM equals to OS minus MS. Again, OM equals to OS minus MS. OM equals to OS minus MS. OS is the radius of the quarter circle, that is X according to our definition, minus MS. MS is 3. So in conclusion, we found out that OM equals to X minus 3 units in its length. OM equals to X minus 3 units in its length. In the next step, we did another construction, that is to say, from point A, we drew perpendicular on OS. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point A and OS as N. So inside quadrilateral NAPS, we have 1, 2, 3 right angles. Therefore, the fourth angle must be also equal to 90 degrees. And we know that any quadrilateral that has 4 right angles must be this rectangle if not a square. So we relate to this quadrilateral NASP as a rectangle because it has 4 right angles. And we also know that the opposite sides of a rectangle are equal to each other. So in rectangle NAPS, side AP equals to the opposite side NS. But AP equals to 6, therefore NS must be also equal to 6 units in its length. Here NS equals to 6 units. Likewise, you know that the opposite sides of a rectangle are parallel to each other. That is to say, side AP is parallel to the opposite side NS. I'll repeat again. In rectangle ANSP, side AP is parallel to the opposite side NS. So we know that AP is parallel to NS. But NS is part of the straight line OS. Again, NS is part of the straight line OS. And if part of the straight line is parallel to another straight line, then the straight line itself must be also parallel to the other straight line. Here, part of the straight line OS is NS that is parallel to AP. Therefore, the straight line OS itself must be also parallel to AP. Okay, here the straight line OS must be also parallel to AP. So, in quadrilateral OSAP, we found out that side OS is parallel to side AP. Therefore, this quadrilateral OSPA that has one pair of parallel sides is a trapezoid. Repeat again, quadrilateral OSPA is a trapezoid because it has one pair of parallel sides. In conclusion, we found out that quadrilateral OBQS is a trapezoid, and quadrilateral OSPA is also trapezoid. So the sum of the areas of those two trapezoids, in total, it is equals to this whole shape. This whole shape AO, BQ, SP. This whole shape. The sum of the areas of those two trapezoids equals to the area of this whole shape in total. Okay? So, in the next step, we found out the length of this line segment ON. What is the length of line segment ON? From the drawing, it is very easy to see that ON equals to OS minus NS. Again, ON equals to OS minus NS. ON equals to OS minus NS. So ON equals to OS, that is the radius of the quarter circle, that is X, minus NS. We already found out that NS equals to 6. So ON equals to X minus 6. ON equals to X minus 6. Here ON is equals to X minus 6 units in its length. In the next step, we focus on the right triangle ONA. On the right triangle ONA, we define this angle as alpha. So in the right triangle ONA, this angle equals to alpha according to our definition. This angle equals to 90 degrees. Therefore, the missing angle must be equal to 90 degrees minus alpha according to the rule that the sum of the angles in any triangle is equal to 180 degrees. But we defined 90 degrees minus alpha is beta. Therefore, this missing angle equals to beta. Okay, so in conclusion, found out in the right triangle ONA, we have three angles. This angle equals to alpha, this angle equals to 90 degrees, and this angle equals to beta. Then we know that angle OAB, this is angle OAB, that is a right angle, it is equal to 90 degrees. So angle OAB, the right angle OAB minus this angle that is alpha must be equal to the missing angle. Again, angle OAB, that is right angle, that is equal to 90 degrees minus this angle that is alpha, it is equals to the missing angle. So in conclusion, we found out that this missing angle equals to 90 degrees minus alpha. But 90 degrees minus alpha is beta, therefore the missing angle equals to beta. So in the right triangle OMB, this angle equals to beta, this angle equals to 90 degrees, therefore the missing angle must be equal to 90 degrees minus beta. But 90 degrees minus beta is alpha. 90 degrees minus beta equals to alpha, therefore the missing angle equals to alpha. In conclusion, we found out that in the right triangle OBM, we have three angles. This angle equals to beta, this angle equals to alpha, and this angle equals to 90 degrees. In the next step, we proved that those two right triangles can go into each other. And we also know what is the definition of line segment OA. Line segment OA starts from point O, that is the center of the quarter circle, and ends at point A, that is the point of the quarter circle itself. So this is exactly the definition of a radius. Therefore, OA equals to X, that is the radius of the quarter circle according to our definition. Likewise, what is the definition of line segment OB? Line segment OB is also the radius of the circle, of the quarter circle, that is equal to X, because it starts from the center of the quarter circle and ends at point B, that is the point of the quarter circle itself. This is exactly the definition of a radius, therefore OB is also equals to X. So we proved that the right triangle ONA is congruent to the right triangle OBM, that those two right triangles can go into each other. So why those two right triangles can go into each other? First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. In addition, those two angles are both equal to alpha, therefore they are equal to each other. And finally, those two angles are both equal to beta, therefore they are equal to each other. So we actually proved that all the three angles in the right triangle ONA are correspondingly equal to all the three angles in the right triangle OBM. In addition, we know that side OA equals to side OB because of the fact that those two sides that are both the radii of the circle that is equal to x, therefore they are equal to each other. So we actually proved that those two right angles can go into each other according to angle side angle rule. What is angle side angle rule? Angle side angle rule is if you prove that two angles and the side that included between the two angles in one triangle are correspondingly equal to two angles and the side that included between the two angles in the second triangle, then you actually proved that the two triangles can go into each other according to angle side angle rule. And in this, in our original drawing here, we proved that those two angles alpha and beta and the side that included between those two angles, that is side OA in the right triangle ONA, are correspondingly equal to those two angles that are alpha and beta, and the side that included between those two angles is side OB in the right triangle OBM. Therefore, we proved actually that those two right angles can go into each other according to angle side angle rule. We have two angles, and the side that include between the two angles in this triangle are correspondingly equal to those two angles, and the side that include between those two angles, that is side OA in the right triangle OBM. Therefore, those two right angles can go into each other according to angle side angle rule. And from the fact that those two right angles can go into each other, we will derive that side ON in the right triangle ONA is equal to side BM in the right triangle OBM. Repeat again, we will conclude that side ON is equal to side BM. According to the rule that corresponding sides that can go into triangles are equal to each other. Those two right triangles can go into each other, therefore the two corresponding sides, that is to say side ON and side BM, must be also equal to each other. But we have already found out that ON equals to x minus 6. ON equals to x minus 6. So we can write here that ON equals to x minus 6. And from this equation, x minus 6 equals to ON equals to BM, we will derive that BM is also equals to x minus 6. Here, this side BM is equals to x minus 6 units in its length. Likewise, because of the fact that those two right angles can go into each other, we will derive that side AN is equal to side ON. Side AN in the right triangle ONA is equal to side OM in the right triangle OBN. Repeat again. Side AN is equal to side OM. But we have already found out that side OM is equal to x minus 3. Again, side OM is equal to x minus 3. So we can write here that OM equals to x minus 3, and from this equation x minus 3 equals to OM equals to AN, we will derive that AN is also equals to x minus 3. Here AN is equals to x minus 3 units in its length. In the next step, I copied the right triangle ONA in a new page and we implemented the Pythagoras theorem on this right triangle ONA. So actually, this is the right triangle ONA that I copied from the original domain. Side ON equals to x minus 6, side AN equals to x minus 3, and the hypotenuse OA equals to x. It is the radius of the quarter circle. So here by PT is the implementation for Pythagoras theorem. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So in the right triangle ONA, it means that OA square equals to ON square plus NA square. Again, in the right triangle ONA, OA square equals to ON square plus NA square. Okay, OA square equals to ON square plus AN square. So OA is x, therefore OA square is x square, and it is equals to ON square. ON is x minus 6, therefore n square is x minus 6 square, plus an square. An is x minus 3, therefore an square is x minus 3 square. So in conclusion, found out that x square equals to x minus 6 square plus x minus 3 square. Here we open the brackets of this side of the equation and found out that x square equals to x minus 6 square. X minus 6 square equals to x square plus 6 square, that is 36, minus 2 times x times 6, that is minus 12x, plus x minus 3 square. X minus 3 square equals to x square plus 3 square, that is 9, minus 2 times x times 3, that is minus 6x. So here we have x square on both sides of the equation. So x square will get cancelled, also we cancel x square. In this side of the equation we left with nothing, so it is 0. That is equal to, here 36 plus 9 is 45. And we have also minus 12x minus 6x is minus 18x plus x squared. So in conclusion, found out that 0 equals to 45 minus 18x plus x squared, or x squared equals to 18x plus 35 x squared. X squared minus 18x plus 45 equals to 0. So this is the quadratic equation, and the general formula for a quadratic equation is ax squared plus bx plus c equals to 0. Here a, b, and c are the coefficients of the quadratic equation, and x is the variable that we are looking for. And we find out the value of x according to the following formula. X equals to minus b plus minus square root of b squared minus 4 times ac over 2a. In our specific quadratic equation, the coefficient a equals to 1, the coefficient b equals to minus 18, and the coefficient c equals to c. So we put the data inside this general formula and found out the value of the values of x. So x equals to minus b. B is minus 18, therefore b is minus 18, that is plus 18, plus minus square root of b squared. B is minus 18, therefore b squared is minus 18 squared, that is 324. Minus 4 times a is 1, so minus 4 times 1 is minus 4, times c, that is 45. So minus 4 times 45 is minus 180, divided by 2. So we found out that x equals to 18 plus minus square root of 324 minus 180 over 2. So x equals to 18 plus minus 324 minus 180 is 144 divided by 2. So x equals to 18 plus minus, the square root of 144 is 12 over 2. So here we have two solutions that are possible for x. Either x equals to 18 plus 12, that is 30 over 2. 30 over 2 is 15. So according to the first solution for x equals to 15. We have also another solution that is possible for x. The other solution that is possible for x is that x equals to 18 minus 12 over 2. 18 minus 12 is 6, and 6 over 2 is 3. So according to the second solution, x equals to 3. But because of the fact that we've already found out that the length of line segment BM is x minus 6, yeah, so BM equals to x minus 6. So BM is a line segment, is a length, and as a length, it must be a positive number. So x minus 6 is equal to the length of line segment BX. It must be a positive number. That is to say, x minus 6 must be greater than 0. If x minus 6 is greater than 0, it means that x is greater than 6. It means that x is greater than 6. So if x must be greater than 6, it can never be equal to 3, that is less than 6. Therefore, we cancel this solution, and we left only with the first solution that is possible for x, that x equals to 15 units in its length. Repeating again, we found out actually that the radius of this quarter circle x is equals to 15 units in its length. X equals to 15. In the next step, I actually presented to you the formula of a trapezoid. What is the area of the trapezoid? Here, I repeat again that a trapezoid is a quadrilateral with one pair of parallel sides. Here we have quadrilateral ABCD, In this quadrilateral ABCD, side AC is parallel to side BD. Therefore, quadrilateral ABCD is a trapezoid. The two parallel sides, that is to say AC and BD, are defined as the bases of the trapezoid. So what is the area of trapezoid ABCD? The area of trapezoid ABCD is equals to the sum of its bases, that is to say it is AC plus BD. AC plus BD, that is the sum of the bases, times the height, that is CD. So the height CD is defined as h, so it is times h over 2. Again, the area of any trapezoid equals to the sum of its bases, that is AC plus BD, times the height, that is CD, that is h, divided by 2. Okay, and what is the area of the green shape? The area of this green shape equals to the area of this shape in total, the whole shape OAPQB, minus the area of this quarter circle OAB. Again, the area of this shape in total minus the area of the quarter circle OAB equals to the area of the green shape. But this shape in total, it consists of two trapezoids. Trapezoid OBQS and trapezoid OSPA. So the sum of the areas of those two trapezoids is equals to the area of this whole shape in total. Therefore, the area of the whole shape in total equals to the area of trapezoid OPQS plus the area of trapezoid OSPA. So the area of this whole shape minus the area of the quarter circle OBA equals to the area of the green shape. Again, the area of the whole shape in total, it is equals to the area of trapezoid OBQS plus the area of trapezoid OSPA minus the area of the quarter circle OBA. So what is the area of trapezoid OBQS? The area of trapezoid OBQS equals to the sum of its bases, that is BQ plus OS. BQ plus OS times the height, that is QS, over 2. So the sum of the bases, that is BQ plus OS times the height, that is QS over 2, is the area of trapezoid OBQS. BQ is 3, OS is 15, the height QS is 9, divided by 2. 3 plus 15 is 18, 18 over 2 is 9, and 9 times 9 is 81. In conclusion, found out that the area of trapezoid OBQS is 81 square units, plus the area of trapezoid OSPA. The area of trapezoid OSPA, the area of this trapezoid OSPA equals to the sum of its bases, that is OS plus AP. OS plus AP times the height, that is SP over 2. Times the height, that is SP over 2. OS is 15, AP is 6, SP is 12, divided by 2. 15 plus 6 is 21, times 12 over 2 is 6. And 21 times 6 is 126. In conclusion, found out that the area of trapezoid OSPA is equal to 126 square units, minus the area of the quarter circle OBA. What is the area of this quarter circle OBA? The area of any quarter circle equals to the area of the circle over 4. And the radius of this, the big circle is x, and therefore the area of the big circle is pi x squared, and if we divide the area of the circle that is pi x squared by 4, we get the area of the quarter circle, this quarter circle OBA. So we found out that the area of the quarter circle OBA equals to pi x squared over 4, x is 15, therefore x squared is 15 squared, that is 225. In conclusion, found out that the area of the quarter circle equals to 225 pi over 4 square units. And 225 pi over 4 is 176.716 square units. So in conclusion, found out that the area of the green shape equals to 81 plus 126, that is 207, and 207 minus 126.716 is equals to 30.285 square units. In conclusion, found out that the area of this green shape is equals to 30.285 square units. Okay, thank you very much.